All right, so maybe we should get started. I guess it's 1:06, so welcome back. This lecture, you guys have read this paper about Amazon, so we wanted to really practice trying to get you guys to talk to each other and discuss this paper a little bit more, to at least halfway try to recreate the experience we might have in person. So the plan is we're going to ask you guys to go into breakout rooms, or rather my Zoom client, I think, will shove you into various breakout rooms here of like 3 students each roughly. And what we'd like you guys to do is discuss the reading question that we assigned about this Amazon paper. And just to remind you, the question is sort of to figure out, these authors are writing these specifications for a fairly complicated system. What's the value to them? Why are they doing it? They're not using it to prove anything correct, which was the value we sort of espoused for specs. So what's going on? Why is this a useful thing to them? And what's the value? Any questions before we sort of move into breakout rooms? And then just to say, we'll sort of give you guys 5 minutes or so in the breakout rooms to talk about this. And then we'll bring you back and we can talk about what is going on, what's the value for Amazon in these specs. And then Butler will tell you more about specifications more broadly and correctness. Make sense? Any questions before we jump in? All right, so let me put a few recent additions into breakout rooms, and then we will be off and running. All right, I think that's that. So let's do it. So I guess just to quickly say, okay, so this is a bit of an experiment. We'll curious to hear from you guys also how this works, if this is useful for you or not, or what we can make, how we can make it better. I think one thing we're curious to hear is actually, let's discuss. So what did you guys come up with in your breakout groups for what's going on with these specs? Why are they useful? Anyone want to jump in? Oh, Amanda, I guess.
Yeah, we were directly talking about the question from the reading. The reason why, like, even though you can't verify the implementation, specifications can still be useful for verifying design. And whether there are any bugs or loopholes or backdoors in your design that you didn't think about, which is usually the main problem. And then it's just a matter of, okay, let's implement our design correctly.
Makes sense. I see Butler smiling about that.
Sounds good to me.
Yeah. Anyone else?
I guess I'll go. Another point that we talked about was how once you have actually verified your design, if you want to go back and change your design or iterate on your specifications, then you can validate that those changes aren't going to introduce new bugs rather than just going straight into the code base. Yeah.
That's a good point. Yeah, evolution seems like a real problem in many of these systems, and this might be helpful. Anyone else's group had other points they ran into, or?
We talked about that this enables a change of mindset. Just we always focus on the happy path as engineers. It's a natural way of designing things, and now just thinking how the system needs to go, or the right properties from the very beginning. That's a powerful tool to define a more well-structured system.
Yeah, indeed. I think perhaps one way to phrase it is like good forcing function to really consider all paths and sort of from a different angle, perhaps. Yeah.
One thing that was brought up in our breakout room was just simply for documentation. And like at a big company like Amazon, with a lot of people probably moving around teams or getting involved with projects, it's a really good way for just having like a high level overview of what a specific tool or component of a system is meant to do. And so just having that for the documentation purposes is valuable.
Mm-hmm. Fair enough. Yeah, it's a good sort of structured documentation that maybe easier to think about writing. Yeah. Anything else you guys discussed?
I guess one thing I wrote was just like having like a different approach to design of complex systems from the beginning. So like someone mentioned like the happy path or whatever for code. But like there's also like, you know, they mentioned the thing about safety and liveness properties, and just like thinking about what does a system even need to like successfully even like run in the first place, like all the sort of things that have to happen first before anything, just to like, you know, catch worst case stuff before, like during almost like design and planning.
Yeah, I guess one of the things you're saying is maybe this would be actually quicker to catch some serious issues this way than going all the way to building a prototype and then discovering it doesn't do what you want.
Yeah, exactly.
Yeah, good point. All right, that seems like a pretty broad range of indeed answers. Covers most of the things I would have thought about probably. Anyone else want to jump in before? All right, so it seems fair enough. So I guess we'll figure out how to run these things maybe better or more interactively. Feel free to like send us email if you think we should do longer breakouts, whatever, smaller groups, bigger. Let us know. We'll sort of iterate. But for now, hopefully this was helpful. And I guess Butler, you want to go ahead and jump in?
Okay, let me see if I can make this work. There we go. I don't need all of that. Okay, so this is the paper that we were reading today, and I'm not going to do what we often have done in these lectures, which is to go over the paper. Instead I'm going to give you my slant on specifications, which has a lot in common with what they talk about in this paper, but there are some variations as well. So it seems good to start by thinking about what specs are for. And I've broken it down into 4 things here. One, which should be familiar to everyone, is that specs are for modularity, so that to decouple the code of a module from the client. And I'm sure you've already encountered this thought many times in earlier courses. A second thing, which is the thing that actually interests me the most, is a spec gives you insight. The spec's job is to tell you what the system is supposed to do for you without distracting you with the details of how it's going about it. In order to achieve this, of course, the spec has to be a lot simpler than the code. And the challenge is to find a spec that is much simpler than the code, but still covers all the ground. And I'll be giving some examples of this on a relatively small scale as we go along. A third use for specs is that you might want to know whether your code is right. And of course, what it means for your code to be right, what it means for your code to be right is that you can, in the strongest sense, you can give a proof that the code actually does the things that the spec says it's supposed to do. And this notion of proving the correctness of code with respect to a spec is actually the main theme of this course. And we'll be studying that in labs with Cox specs. And we'll also be studying it in paper, studying other mechanized formal methods of doing this kind of proof in other papers that we read. And then the fourth thing that a spec can be good for is for model checking. You can, if you have a spec that says at least something about what the system is supposed to do, and then you have some representation of the code for the system, you can use model checking to systematically explore part, usually not all because it's too big, but at least part of the state space. And of course, the Amazon paper put very heavy emphasis on this. And the downside of model checking is that you can never be sure that you found all the problems with model checking because it's only exploring part of the state space. On the other hand, the charm of it is that you can just push a button and use a lot of compute cycles to do the model checking, and you don't have to think about it too much once you've written down the spec and written down the code. That's a little bit misleading. They don't say much about this in the course, but I think people have generally found that sometimes you have to fuss around with your code some, or with the parameters of the model checker in order to persuade it to explore the right parts of the state space. But still, it's a much less labor-intensive process than proof. So I'm not going to talk about model checking anymore. This paper is probably the best view of model checking that you'll get in this course. So what is a spec? How do you go about modeling a system? The quote at the top of the slide is from Leslie Lamport. If you're not writing a program, don't use a programming language. Use something that's more powerful and closer to mathematics. So the basic strategy for modeling any system, which this strategy exists in innumerable variations, a number of which we'll see as we read the papers in this course. The basic strategy is you model the system as a global state with atomic transitions or steps that get you from one state to another. Some of the system state is visible or external. The rest of it is internal. And the job of the spec is to describe what the changes in the external state are going to be. There used to be a lot of people who thought that, no, this can't possibly work because in a distributed system, there is no notion of global state. Each part of the system has its own local state and they communicate by sending messages to each other or whatever. But that's a very low-level implementation, code-oriented view. The God's eye view of there being a global state for the entire system is a perfectly good way of thinking about the system, even if none of the agents in the system can actually see the whole state. Okay, now for a little bit more in the way of concrete details. As the system runs, it goes through a sequence of states, and we call that sequence of states a trace, or maybe sometimes also a behavior or a history. So you start out in state S0, then you go to state S1, then to S2, and so on and so forth. And a spec is nothing more than a set of visible traces, and that set of traces is the behaviors that the system is allowed to display. And we say that a piece of code, often called an implementation, but it takes just takes too long to say implementation. So a piece of code satisfies a spec if the visible traces of the code are a subset of the visible traces of the spec. So what the spec is doing is it's saying what the code is allowed to show you externally. And that's the high-level view. So let's look at a very simple example. Suppose we have a first in, first out buffer with put and get operations. So the external state of this system is two variables, which I've called op and val. And the put and get operations, each in this state-oriented view, each have two visible steps. One of the two steps is to start the operation, and one of them is to complete it. So in the case of put, the way you start the operation is that you set the op variable to put and the val variable to the value x that you want to put. And then you wait for the system to respond by saying, okay, I've done it. And in the case of get, you start a get by setting the op variable to get, and you wait for op to become okay, and then you get the value out of the val variable. So here's a visible trace that shows one thing that might happen. You start out in a state where you don't care what the value of either variable is. Then you set it to put comma 3, the system responds with okay. You set it to put comma 10, the system responds with okay. You set it to get comma 10, system responds, well, you set it to get, you don't care what the value is in that case. The system responds with okay, comma 3, and so forth. So that's the external view of the system. What's the internal view of the state going to be? How is the spec going to describe what the system is allowed to do? Well, internally, the state is going to be a sequence of let's say, of natural numbers, if that's what we're putting and getting. And the put operation is going to append the value to the internal sequence Q, and then it's going to set the op to okay. And the get operation is going to take the head off the queue and put it into the val variable. It's going to set Q to the tail, and then it's going to say OK. So those are the internal operations of the system. If there's things about what I'm saying that are not clear, you should just unmute yourself and ask a question, please. Because what we just did was the foundation of everything that's going to happen in the rest of this lecture, and a great deal of what's going to happen in the rest of the course. So if there's something about it that's not clear, now would be a good time to ask. Okay, so the Amazon paper describes how they use TLA. They don't give a lot of detail about TLA, and I'm going to give somewhat more of it here. So the idea of TLA is that the way you describe an action is a set of possible steps. So consider the action x gets x plus 1. That is a summary of the steps. X equals 0 goes to x equals 1, x equals 1 goes to x equals 2, and so forth for all the natural numbers. So it's actually an infinite set. And the basic idea of TLA is that the way you describe an action is with a predicate on the current state and the next state. So how do you do x gets x plus 1 as a predicate? The answer is, it says the new state of x is equal to the old state of x plus 1. So we write that x prime, we write primes for new states. X prime equals x plus 1. That is the predicate that describes that particular action. Of course, there's going to be a little more to the predicate because there's other variables, and you have to also say that the other variables don't change. We're going to gloss over that for now. So if we want to write that out in more explicit detail, we'd say this is short for the new state is the same as the old state, except that the value of the variable x prime is x plus 1. If you have several actions, for example, the put and get actions of the buffer, then you use OR to combine them. That says the system can either do the put action or it can do the get action. Now, in any particular situation, if you go back and look at how those actions were defined, only one of them is going to be enabled, because the put action is only going to be enabled if the op variable gets set to put, and the get action is only going to be enabled if the op variable gets set to get. But in general, more than one action might be enabled. And in that case, we have what's called non-determinism. You don't know for sure what's going to happen next. And this business of non-determinism is usually the thing that causes the most trouble. Usually the thing that causes the most trouble in thinking about systems at the level of specifications and high-level code. Concurrency, of course, is a special case of non-determinism, because the whole idea of concurrency is, as you're accustomed to thinking about it anyways, you've got multiple threads, and each one of them has something that it would like to do next, and you don't know which one is going to run next. Except in the rare case where only one of the threads is unblocked. So that's the way you put actions together to make up all the, to tell all the different things that the system can do. And to compose systems, you use the AND operator, usually with some shared state. So in the example of the buffer, for example, the client is going to trigger the put and get actions by setting op. And the final piece of conceptual machinery that you need for TLA is the notion that you have an invariant that defines the reachable states of the system. In the put and get example of the FIFO buffer, probably all the possible states of those variables are reachable. But in general, that's not going to be true, and we'll see some examples of that as we go along. Okay, the other basic high-level thing to know about writing specs in this style is the difference between safety and liveness. So safety tells us what the system is allowed to do, in particular that nothing bad happens. If a system violates safety, it does so by doing something bad at some definite point, that is, in a finite trace. Liveness says what the system has to eventually do. Or to put it another way, it says that something good eventually happens. And in general, no finite trace can violate liveness, because there's always could be more transitions in which the good thing happens. for the kind of program that you're probably accustomed to thinking about from your own personal experience, it's a program that you feed it an input, it does some computation and produces an output, and that's the end of it. In that case, safety is what's called partial correctness, which says if it never gives the wrong answer. And liveness is what's called termination, which says it actually does give an answer. It finishes as opposed to looping indefinitely. So that's safety and liveness. For the most part in this course, we're going to concentrate on safety. And the reason for that is that usually safety is really what you care about. It's not that interesting to know that your system is eventually going to deliver a message. You actually want to know that it's going to deliver it within 2 seconds or whatever your notion of promptness is. And of course, whether the system delivers a message within 2 seconds is a safety property. Because all you have to do is wait for 2 seconds, and if it hasn't been delivered, you know that it's bad. A slight digression. Usually when we talk about the transitions of systems, we don't talk about them in terms of state changes. We talk about them in terms of operations. So we name the visible transitions as operations. So S0 goes to S1 via operation 1, which goes and so forth. And we use the names of the operations as the trace. So for example, in the FIFO buffer with its 2 variables, I've written down here a prefix of the trace that I showed you a couple slides back. And in this system, of course, the operations are put of x and get returns x. And each of them has 2 steps, as we saw before. And the example now becomes quite a bit more intelligible. Instead of a lot of futzing around with the op and val variables, the trace just becomes put 3, put 10, get 3, put 15, get 10, get 15. And the way I like to think about this is the charm of the state-oriented view is that it's the simplest. If you want to do things in terms of operations, there are various technical details that you have to worry about. But the way I think about it is, what I just showed you on this slide is a calling sequence for the put and get operations, where the calling sequence in particular consists of setting the op and val variables to appropriate values and retrieving appropriate things from them. And this is very similar to what you have inside the computer. If you want to, you think in terms of calling a function, but if you look at the machine code for that, what it actually does is it loads up, it makes state changes to the machine. It loads up various registers and stack locations and so forth with arguments. And then it changes the value of the PC and so on and so forth. And typically, that mechanization of a function call is also called a calling sequence. So it's exactly the same idea. Okay, now I want to spend a little bit of time talking about the stages of design and verification of the system at a very high level. The first thing is you have to write the spec. If your system doesn't have a spec, it cannot be wrong. It can only be surprising, because how would you know that it's wrong if you don't have something to compare its behavior against? So the first step is to write down the system state. And typically, you'll probably find that actually this is conceptually the most difficult thing to get your head around. And we'll see some very simple examples of this as I go along today. And we'll see a lot more examples in the labs and in the papers that we read. The reason writing down the state is hard is that it's difficult to shake your mountain loose from the implementation state and actually figure out what it is that's really going on. And this is why this style of writing specs, this is one of the reasons why this style of writing specs gives you insight into what's going on in the system. Because it forces you to articulate what it is that's really happening from the user's, from the client's point of view, as opposed to getting lost in the details of the implementation. And the second thing is you have to write down the interface, the possible state transitions. So in the case of the FIFO buffer, we had put and get operations, and the spec described what they do in terms of changes to the internal sequence variable. if you wrote code for a FIFO buffer, you might very well find that you had multiple sequences that you chained together, and maybe there's provisions for making some of them persistent and all kinds of other complicated things, which might be very important for the functionality and performance of the system, but they're not relevant for understanding what it does from the client's point of view. Of course, you'd like to know that the spec you've written is correct. And this is something of a challenge because you don't have anything to compare it against. So in some sense, there's not going to be any systematic, convincing answer to the question of whether the spec is correct. The best single strategy for it is to keep the spec simple, because that way you maximize the chance that you actually understand what's going on, and then you can figure out whether what's going on is what you actually want. Well, one example of a way to keep a spec very simple is to say that the spec just consists of some kind of property, such as, for example, memory safety. The system never addresses memory outside of the bounds of the particular variable that it's supposedly updating. And we'll see some examples in the papers that we read of people that are focused on this kind of property as the thing that they're going to prove about their code. Of course, if you work at the level that the Amazon people do, or at the level that I was talking about with the FIFO buffer, to take a much either simpler memory safety is not very interesting because there's not very much, neither the spec nor the code has actually anything to say about memory references. A contrast to this way of getting simplicity, which is to just try to demand that the system satisfies some property, is to demand functional correctness, in which the spec actually gives all the allowed behaviors of the system in detail. Okay, so that's the story for specifications, the specification part of design and verification. First, you write down the state, then you write down the interface. Now, what about the code? So you'd like to know, what you'd like to know about the code, of course, is it correct? What does it mean for the code to be correct? Well, I think I mentioned this before, but now we're going to focus on it. Correctness of the code means that the traces of the code are a subset of the traces of the spec. Now, for this to make any sense, the spec and the code have to have the same external interface. That is, the external state has to be the same, or the externally visible operations have to be the same. Sometimes this identity is achieved by doing some kind of transformation, but we won't go on the details. So, for example, in the case of the FIFO buffer, the spec is written in terms of these abstract op and val variables, but the actual running code is going to have memory locations, presumably corresponding to these values. And so we have to make some sort of, have to tell some sort of story about how to map the memory locations into the abstract variables, but I'm going to ignore those considerations. So the basic idea for proving that the code traces are a subset of the spec traces, of course, it's got to be some sort of induction. And here is the guts of the induction. You show that, looking at the bottom half of this diagram, you show that, I have a gizmo. Let's see if the gizmo will work. Oops, it's not working. Here we go. There we go. Look at that. Yeah, great. Now the only problem is we're on the wrong slide. Hey. There we go. Yes. All right. There we go. Look at that. Look down here. What this diagram says is that whenever the code is in some state C, and it does the transition to some state C prime, then there has to be a function that maps C into f of C and C prime into f of C prime. So And it has to be the case that the spec can make a transition from f of c to f of c prime. So that tells you that this code corresponds to the spec for one step. And then induction says, chain this together and start in some appropriate initial state. And then that shows that for every possible trace of the code, there's a corresponding trace of the spec.
One question.
Yes.
So the horizontal lines that are right there, that's drawing from C to C prime and from F of C to F of C prime,
Yeah.
like, do those have to be the exact same thing? Like, for instance, let's say if like our function was like f of x equals x plus 2, right? And you put like c in, and c is equal to 0, and c prime is equal, let's say, to like 3, right? Would it have to be that you're adding 2 in both cases? Or is it just a similar function? Like, I don't know if that question makes sense.
You have to have an abstraction function that systematically across the entire behavior of the system. You have to be able to write down a single abstraction function that maps the states of the code up to the states of the spec.
Okay, but does the transition, like the horizontal line in this case, from the pre-state of the code to the post-state of the code, need to be the exact same thing as the pre-state of the spec to the post-state of the spec through a function?
It has to be the same thing in the sense that the states match up. So for example, no, but why don't we hold off on this question for a few slides to
Okay.
a more interesting example of an abstraction function.
Okay.
And then I think perhaps it will become clearer, and if it's not, then you should ask your question again, okay?
All right, sounds good.
And the other thing we can learn from looking at this picture is the importance of the invariant, because the job of the invariant is to define what the reachable states are. So for example, suppose you have a piece of code that maintains a sorted array and does binary search to look up at something in that array. It's an essential property of that code that the array A remains sorted. And you won't be able to show that it does the right thing unless you can show that the array is always sorted. So in particular, what that means is that when the code makes transitions, it only has to be doing the right thing for the states that are actually reachable. That is, in this example, for the states that satisfy the invariant that the array is sorted. If the array isn't, then the code might do all kinds of other things. But we don't care about that because the invariant tells us that the code can never get into those states.
Quick question, Professor.
Yes.
So our spec is going to be a finite state machine? Or...
Well, it's not finite state, but it is indeed a state machine.
Okay.
Of course, in the physical computer, it's going to be finite, but that's not very interesting because the number of states in the computer is too big. So you want to think of it as a state machine that's not finite state, which means that all the things you might have learned in a algorithms class about how to do things with finite state machines are not going to be very useful.
Thanks.
Okay, so we back now to what the stages of design and verification are. We already did the first two. We write down the state, we write down the interface. That's the specification. Now, in order to actually do the proof, you have to write down the abstraction function. And then you can actually do the simulation proof that I discussed on the previous slide. What the abstraction function does is to give you insight into why it is that the code works. In addition to that, the abstraction function is an essential part of the proof. So an obvious question to ask is the abstraction function correct? And unfortunately, the only way to convince yourself that the abstraction function is correct is to actually do the proof and see that it always does. The particular abstraction function that you've chosen actually makes the simulation proof possible. And this is unfortunate because doing the simulation proof is a lot of work, since you have to consider every action from every reachable state and check for each one of those that it's actually that the abstraction function actually maps to a legitimate legitimate step of the spec. And in my personal opinion, this work is seldom worthwhile. It's by far the largest amount of work in this whole sequence, and you get the least payoff. So you're only going to actually do these simulation proofs for situations where it's absolutely critical that the code be correct. And we're going to look at some examples of that when we read papers. And we're also going to do some concrete examples in the labs. But I don't want you to come away from this course thinking that the only criterion for the success of formal methods in systems is that you can do these, that you can complete these proofs. Because doing the complete proof is usually not going to be worthwhile. And in fact, my personal opinion is, as you go down this sequence of steps 1, 2, 3, and 4, each successive step is more work and delivers somewhat less value. And the fourth step is by far the most work and delivers by far the least value. And certainly, if you remember from the Amazon paper, they subscribe to this doctrine because they don't even think about doing proofs. And furthermore, they're not even working on the actual running code either. They're working on some high-level pseudocode description of the algorithms that they're trying to convince themselves are going to work. So in particular, they're doing model checking. The Amazon guys say, for us, model checking dramatically beats proof. And there's basically two reasons for that. One is that it's automatic. You just push the button and use up a lot of cycles on AWS. And the other is that experience tells them that it actually finds most of the bugs that they think are going to be hard to find by the other techniques that they already have deployed. And I just want to emphasize this is a very different use of the whole apparatus of specs and abstraction functions than the formal correctness proofs that we're going to be doing in the COC. It's less conclusive, but it is also has the advantage of being much cheaper. Okay, let's look at some concrete examples now, specifications, and in at least one case, we're going to actually look at code. But first, we're going to look at some specs. So here's a reliable two-party channel. There's a type called message. It has two fields called from and to, which are addresses, and it has a body, which I've just described as a string. And a channel is just a sequence of messages in this spec. And there are two operations, send and receive. Send tacks the message on the end of the channel sequence. And receive says, if you can take something off the head of the channel sequence, then you can return it and let the channel sequence be the tail of what it was before. So that none of that should be too surprising. To go any further, we need to have a little bit of notation so that we can write things down precisely. The first piece of notation I'm going to introduce is what's called a set comprehension. And one way to think about set comprehensions is they're a way of avoiding loops and recursion, which is a good thing because typically if a spec involves a loop or recursion, it's much more difficult to figure out what it's actually saying. And the set comprehensions bring things up to the surface that are hidden in the details of loops and recursion in the code. So the canonical thing you have here, oops, sorry. Do I have to turn this on again? Apparently. Yeah, the canonical thing you have here is the set of x's in some existing set S that satisfy P of x. The set of values in x such that P of x is true. So for example, if S is all the integers and P of x says x is a prime, then this set is going to be all the prime integers. A variation on this is that you don't return all the x's, but you apply some function to them. So you write the set of x's. The set of x's such that P of x is true, and then the values are going to be some expression involving x. So let's look at an example here. the function I've written at the bottom of the slide is permutations. It takes in a sequence Q, and it gives back the set of sequences Q prime such that the range of Q prime is the same as the range of Q. That is, the contents of the sequences is the same. And for every T in Q, the number of T's in Q prime is the same as the number of T's in Q. So that should give back a set which is all the possible permutations of the sequence Q. The reason I made this a sequence rather than a set is that there might be duplicate elements. And this definition used a lower level operation called count, which just counts the number of T's in a sequence. So it says it's the number, you make the set which is all the i's with the property that Q sub I equals T, and you return its size. That counts the number of T's in Q. Oops. One other piece of notation is introducing variables. So in the state, if we write it, we're going to introduce a variable x, which is in some set and satisfies some predicate, adds that variable to the state. And the value is going to be arbitrary except for the constraints that were imposed on it. That, i.e., the variable, the value's got to be in the set, and p of x has to be true. In an action, var adds a local variable. So here's the canonical example. You have var x in S such that p of x in set y to f of x. So this is the same thing. If I write this out as a TLA predicate, it's going to say y prime is a member of the set of x's which are in S, satisfy p of x, and then we return the f of x's. Which is another way of saying it is there exists some x in the set such that if p of x is true, then I'm not sure what's going on. I think I made a mistake here at the bottom. Don't worry about it. But the important thing to notice about this construction is that it's non-deterministic. It says that the variable is going to take on some value in S that satisfies p of x, but it doesn't tell you, if there's multiple values, it doesn't tell you which one. And this is the most general form of non-determinism that will show up again and again in specs and high-level code. So to see how that goes, let's look at a sort procedure. You feed it a sequence of T's called Q, and you introduce a variable Q prime, which is also a sequence of T's, which has the property that Q prime is one of the permutations of Q, and for every I that's in the domain of Q prime, either it's 0 or Q prime sub I is bigger than or equal to Q prime sub I minus 1. In other words, the sequence is increasing. So you choose some such Q prime and then you return it. In this case, if it's a total order, then Q prime is going to be unique. But of course, in many sorting applications, the comparison is not being done on the entire value, but only on some field of it. So there might be duplicates. And this spec doesn't say anything about how you should order how you should order values where the field that you're sorting on is equal. And I left the permutations and count guys on there to make this complete. So just a couple more words about sequences. I hope you're starting to get the idea from the examples that we've written down so far, that with these notions of sets and sequences, we can say very precisely what we expect a system to do in a way that's extremely concise. And once you get used to the notation, very easy to read and understand. So what is a sequence? A sequence is a function from natural numbers to some type t. The domain is the domain of the function is the indexes of the sequence, which for this example of a sequence Q, which is just ABA, the domain is going to be 0, 1, 2, because those are the indices that are defined. The range is just going to be the set consisting of A and B, and the size of the sequence is 3. No big surprise. What's going to be somewhat less familiar to you is this notion of composition. Because a sequence is a function, you can compose it with some other function. So Q composed with F is going to be F of Q0, F of Q1, up to F of Qn. You probably know this under the name of mapping F over Q. The little picture shows you what's going on in terms of composition. And as usual, you have head and tail and last and body and plus for concatenation. Nothing new there. So now let's look at the reliable two-party channel. Now that we have a little bit more notation. So the stuff in gray we already looked at, but now we're going to allow crashes to happen. It's possible for either the sender or the receiver to fail. What happens to this channel when there's a crash? Well, the spec says you find some subset of the domain of the channel. That is, you pick out some subset of the messages that are in the channel, and you just keep those. So why does it say that? It says you take that subset that you chose, you sort it, and then you compose it with the channel. So remember what we saw in the previous slide. Composition maps the sequence 5, 7, 9 to the sequence you get by applying square to each of 5, 7, and 9, thus 25, 49, and 81. So in this case, you're going to take the integers which identify the messages that you're going to keep, and you're going to compose that with the channel, and that's going to result in a new channel which just contains the messages that are being kept. And notice that this is highly non-deterministic. All we said about the keep set is that it's a subset of the domain of the channel. We didn't say anything more about it. So the subset might be empty, for example, or maybe nothing is lost off. Keep is equal to the domain. So this is a precise model for the possibility that in the case of a crash, some unknown number of messages are going to be lost. Now, what about asynchronous messaging? Make things a little bit more interesting. Here, the notion is that the channel is capable of dropping, i.e. losing a message at any time. It can deliver the messages in any order, and it can deliver the same message any number of times. This is the underlying model for UDP on the internet. It's the basic packet delivery model for the internet. So we have messages as before. We have the channel. Now it's not a sequence anymore. It's a set, because the internet doesn't guarantee to preserve the ordering of the messages. Send adds the message to the set, and receive says, if you can find a message in the set which has the right to address, then you can return it. And this receive does not drop the message from the channel, because the channel is, we know that the channel is capable of duplicating messages. And that's being modeled in this receive operation by saying that when the receive occurs, we don't take it out of the channel. So it could occur again. But there's also an internal non-deterministic drop action, which says that if there's a message in the channel, you can take it out. So this is the abstract model for packet delivery on the internet, and for many other examples of unreliable asynchronous messaging. Okay, a little bit more notation. We saw sequences. Functions, of course, are more general than sequences. A function, we write a function f:(t_rou), to mean that the function takes a t and returns a u. And implicit, this isn't always going to be true, but implicit in what I say is the function also might return none if it's not defined on its argument. So another way to think about a function is that it's a set of ordered pairs, as you learned in high school math, where all the t's are different. So it's the set of tu such that u equals f of t and u is not equal to none. Composition, we saw that in the case of the sequences, and here it is in general. F composed with g is the composition. First you do f, then you do g. So it's g of f of x. If you want to change the value of a function, here's the basic notation for that. F brackets x gets y is the same function as f, except that at x, its value is y. And the final fragment of notation is quite often it's convenient to write f of x as x dot f. There's fewer parentheses, and it reads better because you can think of it as x dot f dot g. You can think of it as on x. First apply f, then apply g. And you can keep on doing that for as long as you want. People that are really into functional programming don't have any trouble with g, f, x, but I find it difficult. Okay. So now we're ready for perhaps a more interesting example, which is files. So what's the spec for a single file in a vanilla file system? Here's the simplest possible form of it in the 4 lines at the top. A file is just a sequence of bytes, and we have a variable f, which is a file. We're just specifying one file here to keep things simple. So what can you do with a file? You can do read and write. Read of I says return f of I, and write of I and b says f becomes what it was before, except that the value at I is equal to b. So f only changes at its ith element. Of course, you know that if you do a write in a Unix file, it's not quite that simple because the write might extend the file. So here's a somewhat trickier spec, which you might find a bit confusing. It says we introduce a variable f prime, which has this a domain, which is the domain of f plus all the integers between 0 and I minus 1. So in case I minus 1 is bigger than the length of, in case I is bigger than the length of f so far, we're going to extend the domain. And then for every j in the domain of this f prime sub j is going to be, if j equals I, then it's going to be b. That's the byte that we're writing. Otherwise, if j is in the domain of f, then it's going to be f sub I, and otherwise it's going to be 0. So this is extending with 0 if you write beyond the current end of the file. And then having constructed this f prime, in this case, it's completely deterministic, by the way. Having constructed this f prime, then we assign it to f as the job that write does. And the new piece of notation here is I dot dot j is the sequence I plus 1, blah, 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 to j. So for example, if you want the I to j subsequence of a sequence q, it's I dot dot j composed with q. Okay, what about crashes? We know that in real life, things are not that simple, and we're going to see lots of stuff about crashes in the labs of this course. So here's just the beginning of it. Remember, what we're doing here is we're writing a spec, we're not writing code. So here's the spec, the first correct spec for a file system with crashes that you're likely to think of writing. There's going to be 2 variables, the f variable that we had before, and another variable which is I've called f stable, which is you should think of as the file as of the last sync operation. Read is the same as before, write is the same as before, and sync copies F to F stable, at which point all the writes become stable. What does that mean? Well, what it means is summed up in the definition of crash, which says you're going to keep some subset of the values of the domain of F. And what are you going to do with that kept subset? Well, F is going to become F stable overlaid by F restricted to that keep set. In other words, F dot restrictive keep is going to be F, which is only defined on the set, on the keep set. So any place where the keep set says you should keep the new value, we're going to keep it and clobber the value of F stable. Everywhere else, it's going to be the stable value. And then having done this, crash does the sync so that now F stable is the same as F. And I've written explicitly the definition of restrict down at the bottom, but there shouldn't be anything surprising there. It's just telling you that it's only going to be defined on the set, on the keep set. So this definition says every time there's a sync, you have a stable value for the file, and every time there's a crash, you can discard any part of the new file and put it back to what it was at stable time. Oops, sorry. So here's another way to write the crash spec, which is at first you will probably balk at, because you'll say this is ridiculously expensive, since this spec says you're making lots of copies of the whole file. But you have to remember the goal of a spec is to be as clear and simple as possible. And there's no notion of cost for a spec. We're not executing these lines of code. There's going to be an implementation that we are going to, there's going to be some code that we have to show behaves in the way that the spec says, but we do not have to actually do the things that it says in the spec. So here, instead of having F stable, we're going to have a history, which is all the past files, all the possible files that could exist after a crash. And what a write is going to do is it's going to update F in the vanilla way, and it's going to add to the history. Well, what is it going to add? It's going to say, take all the possible files before this write that are in the history and update each one of them with this change. So that adds to the history all the possible new files that existed before, each one with the available change. And we took the union here, so we still have all the files that existed before the write as possibilities. Sync truncates the history so that it just consists of the file F. And then what crash does is it just picks one of these possible files out of H and puts it into F. So this code is, this spec is somewhat shorter than the previous one, and it's also what's the right way to say it? It's much more flexible. It can be extended in a variety of ways, much more easily than the spec that keeps talking about the individual bytes. All right, so much for specs for files. What about code for files? Well, here is the sort of the guts of the code for a Unix-style file system. So we're going to introduce a few types. Block is just going to be a sequence of bytes. That's a disk block. And address is going to be a natural number. That's going to be a disk address. And an inode is going to consist of some data, which is a sequence of these addresses. That's the index information. And a length, which tells you how many bytes there are in the file. And the code representation of a file is just going to be a natural number, which you should think of as an inode number. So there's two variables in this code. There's the so-called file system, which for each inode number tells you the corresponding inode. I decided to change the name from IND to inode. Sorry about that. And then the disk tells you for each address what the contents of that part of the disk is. So there's two parts to the file system state in this spec. There's the inode number to inode mapping, And remember, the inodes give the index information for the file. And then there's the disk, which is actually modeling the physical contents of the disk. And this file system has an invariant. Sorry, it's not the invariant. This file system has an abstraction function. And what is the abstraction function? It says, let the inode be remember, the concrete file is FC and the abstract file is F. How do we get from FC to F? The answer is you feed FC to the FS component of the state. That gets you the inode. So the inode is going to be just the data, which is the sequence of addresses, and the length. Now we're going to have a local variable D, which we get by taking the inode data and composing it with the disk sequence. So that the inode data, remember, tells you how to get from the inodes to the disk addresses. From the inode tells you how to get from the indexes in the file to the actual disk addresses, and then the disk tells you how to get from the disk addresses to the data. So inode.data composed with disk gets you, that's a sequence of data blocks, which are the actual contents of those disk blocks. And then we're going to fold it with plus, which is concatenate. So fold is just going to concatenate those guys together. So that gets us D, which is the contents of all the disk blocks that are implementing the file. And then we don't want all of that. We only want the ones that are actually in the file. So that's from 0 to inode.length minus 1, composed with D. So that's the abstraction function, tells you how to get from the concrete file, which is just the inode number, to the abstract file, which is the sequence of bytes. And this is just repeating what I said about, well, amplifying what I said about fold. Fold F over Q is just the QIs combined with F. So it's Q0 function Q1. F is a binary function. You take F of Q0 and Q1, and F of that and Q2, and F of that and Q3, and so forth. So for example, fold over of plus over 579 is 5 plus 7 plus 9, which is 21. And in the previous example, oops, sorry. Not used to the fact that there's a substantial delay when I switch slides. In the previous example, fold was taking all those data blocks that we got off the disk and concatenating, sorry. Fold was taking all the data blocks that we got off the disk and concatenating them together into one big sequence of bytes so that we could then pick off the appropriate prefix from it. Okay, and maybe this would be a good place to stop and invite more questions. Amanda, did you get your question answered?
I think so, yeah.
Good.
Makes sense now.
Other questions? Okay, well, we'll finish up with a bang with this somewhat complicated example. This is a spec for a bunch of threads that are doing single byte writes into a file in an unsynchronized way. So the idea of it is that and the question that it answers is, if I'm another thread that's looking at this file, what values might I possibly see if I don't know anything about the order in which the threads are doing the writes? So the idea of it's similar to what we did with the history in trying to understand what can happen after a crash. Oh, by the way, I should mention, of course, in real life, the way the spec was written, it said that any subset of the bytes that got written since the last sync could be lost. Of course, in real life, file systems work with a granularity of disk blocks. So it's not possible to lose the consequence of an individual single byte write. You can only lose things with the granularity of whole blocks. This is a good example of a situation where you're making a mistake by putting that kind of detail into the spec. It makes the spec significantly more complicated. See, the way the spec was originally written, it doesn't say anything about disk blocks. Everything is written in terms of bytes. And there's no doubt that if you restrict the losses to the granularity of blocks, that's going to be a subset of the things that can happen here where the granularity is bytes. So why do we write bytes instead of blocks? Well, two reasons. Well, three reasons, actually. The most important reason is that it's simpler to write it in terms of bytes. The second reason is that you shouldn't be depending as a client on the fact that it's actually blocks rather than bytes. That's going to lead your thinking down very unhelpful paths. And the third reason is, of course, the underlying implementation might change its mind about what the block size is. And then if that were showing through if the block size isn't showing through into the spec, it's probably not useful at all because it might be 1 byte. And if the block size is showing through into the spec, then it's constraining the code to only use that block size, or maybe perhaps to only use that block size and bigger block sizes. And that seems like a bad idea. So this is a very simple, but I think also very clear-cut example of how you want to suppress implementation details in the specification. All right, back to this weird example of non-atomic writes. Why is it not? There we go. Not that. There we go. So the idea here is the threads are going to be abstracted as these ops. The notion is that each thread is doing some concurrent write to a bunch of different bytes, one at a time. And we have the file F and the history. And what the history now is going to be is for each op, it's going to tell you what the old file was before the write and what the new file is. And what a write is going to do is it's going to say is if the op is a new one, if this thread hasn't been writing this file before, then the old file is F and the new file is F2. And then it's going to change F sub I to BB as we always had. And then it's going to change the new field of the op at byte I to be B also. So what that says is that for each file, we're keeping track of all the different things that this thread has done to it. And how is a read going to work? Well, that's the trickier part. Down at the bottom of the slide, there's a function called mix. And I'm not going to try to go through it, but what mix says is you've got a bunch of sequences of T. Those are the files. You've got a bunch of files, one from each thread. And you get to pick 1 byte from each file in a completely non-deterministic way. And mix computes a sequence. It's all the possible files that you could get by picking bytes from all the different inputs. So that summarizes the notion that you don't know anything about what subset of all the writes that have been done is you're actually going to see as part of the read. And of course, again, in real life, if you're communicating with the threads that are doing these writes, you would have more information than that. You would know, for example, that if Nikolai writes 0 into byte 10, and then he tells me that he's done that, then when I read byte 10, well, it might not be 0 because maybe someone else wrote it too, but it's definitely going to be different from what it was before. But we're suppressing that information in this spec, but we're allowing more behaviors than we know the code would actually display. In the same way as before, when we were looking at things at a byte granularity rather than at a block granularity, we suppressed that information and we did everything with bytes, even though we know that the code isn't going to actually do that. And again, the reasons are the same. You want to keep things as simple as possible, and you want to make as few assumptions as possible. If we want to put in information about which threads were communicating with which other threads, that would make the spec a lot more complicated. So anyway, the idea here is you pick an F prime from the mix, and then you return the ith byte from that F prime. And when you're done, you erase all the ops so that all you have is F. So this is a completely precise and relatively concise account of a fairly messy situation. And the thought that it should probably be inspiring in you is that you don't want to be there. You don't want to be in a situation where a lot of separate threads are doing non-atomic concurrent writes to a file, because you're really not going to know where you are. And on that note, I think that I will wrap this up, and I'd be happy to entertain more questions. By the way, I will post these slides. In fact, I have posted these slides to the lecture notes section of Piazza. Other questions? Everyone is stunned. Okay, then I guess we're done. See you next Tuesday.